Okay, we are going to talk about water today. So a lot of the stuff about water we talked about during our walk last Thursday. So hopefully this will be bringing back memories from the walk a week ago. So first, a question relevant to yesterday's lab activity. Jessica? Class? A question relevant to yesterday's lab activity. Where are you not likely to find a volcano?
I want to say E. But I don't remember really talking about like the different type of boundaries, though. I think it's E.
Okay, so let's talk about the ones that we can absolutely rule out. What can you absolutely rule out?
Hotspot.
Okay, hotspot. Because hotspots are places where you have a magma chamber that comes up through the mantle making a volcano. Where's the hotspot we talked about in lab?
Didn't we talk about like the Hawaiian
Hawaii. The Hawaiian island chain is all the result of a single hotspot. There is another hotspot much closer to home. Yellowstone. Yellowstone has a huge magma chamber, and that's why you have the geysers there, because you have the heating of water underground. You have they've got some pools that are scalding hot. A few years back, a guy was walking off the path, fell in, and died, cooked to death. And that has erupted many times in the past, but it's not a nice, smooth flow when it erupts. So what would we call the kind of volcano if it had a nice, smooth flow?
That one is the magma
Shield.
And it's cinder.
Cinder cones are when they're violent.
That's the next question, guys.
Well, the eruptions now I've lost my memory of what of that place up there in Wyoming and Yellowstone, the place I'm talking about right now, have been very violent. So the areas like from there, I mean, here we're definitely in the debris field from it and goes much farther to the west when it erupts. Go ahead, Bryson.
I hear that, is it Mount St. Helens in Washington?
Yeah.
It erupted when I was in high school.
I hear there's one that's supposed to be like a doomsday effect.
That would be Yellowstone.
That one.
Oh, yeah.
And so,
There's something I think it's
Like everything's dead.
yeah, we watched like a movie about it in like 8th grade science or something, and it was like of it.
so if Yellowstone erupts, we are going to have a hard time living here. You know, we might not make it out. It depends on the eruption. But if you go to western Nebraska, there is a place, and of course my brain is just not working today, where they have excavated a lot of fossils that were buried in an eruption of Yellowstone.
But wouldn't western Nebraska be closer to Wyoming?
It is indeed closer to Wyoming. That is right.
Wait, is that because all the soot lands, or is that
Yes.
because wow.
Yeah, it's that the ash goes up in the air and then it falls out of the air. And if you have an eruption, it goes higher, travels farther. And so they have maps showing where the large amounts of ash have been deposited in previous eruptions based on excavations. And I believe that we are in the range where they would expect us to be receiving heavy ashfall.
So would southern Colorado be affected by it?
Not so much. It's not in the direction the wind blows.
So you wouldn't be affected?
I don't think we would be in trouble, no.
What about Ohio?
No, you're too far away, probably. You would probably still get some, but it wouldn't be like, we can't leave our house today because the doors are cemented closed. Okay, so hotspots, definitely not correct. What's another one that we talked about would be definitely a place where we find volcanoes?
I want to say A.
Okay, convergent boundaries. Convergent boundaries are the places where we talked about the plates coming together, one sliding under, subducting, grinding and melting material that makes us have volcanoes. So then we're left with transform boundary and divergent boundary. Now, a transform boundary is a boundary where they're moving like this with respect to each other. A divergent boundary is where they're moving away from each other.
So then C is the answer, because B would be the rubbing together of them, and wouldn't that still create a hot spot?
There would be some rubbing, but this comes from the textbook. That's the one I would choose for the correct answer, so is the transform boundary, because you're not having a significant amount of grinding there. The divergent boundary is opening up a gap, and so you have magma that comes up there. Now, it's not going to be a violent volcano probably, because that kind of magma is the kind that flows. But you have lots of mid-ocean vents and things like that, which are essentially volcanoes.
What do the arrows for convergent boundaries?
That's so you have plates that are moving away from each other if it's divergent.
No, convergent.
Oh, convergent, it would be like this. The plates are coming toward each other.
Oh, yeah.
All right, so getting to the water. So statistics that we talked about during our walk last week. 97% of all of Earth's water is in oceans. Only 1% is available for us as water vapor, groundwater, and freshwater, things that we actually might want to drink. And so here's the total breakdown that we talked about during the walk that I had written on my hands. And surface water, 0.009%. That's the water we see in streams, rivers, lakes, not oceans, because the oceans are in the saline.
The floods, is that surface water or groundwater?
It would become surface water when it's flooded. So where did it come from? If you're talking about the current floods, that's surface water all the way. But if you talk about like the biblical flood, it's believed some water came from below and some from above. And in fact, recent research, and this recent research is looking at diamonds, shows that diamonds that were formed deep in the mantle, deep in the crust, close to the Mohorovic discontinuity, have water in them, small amounts of water. But it is hypothesized based on that there is more water down in that region, the region of the boundary between the crust and the mantle, than we have on the surface of the Earth.
It's like the journey to the center of the Earth.
Yeah, so they hit the water region.
There's dinosaurs down there.
Sure. So that's something that's really interesting to me. It seems maybe a little too strong of extrapolation to say that there's that much water down there, but they do have evidence of H2O molecules there. Okay, moving on. The hydrologic cycle. We talked about this in the walk. It's driven by the sun. Heat from the sun causes water to evaporate, and that evaporated water then goes up into the sky, where it condenses and falls back as precipitation. Gravity is what brings it back down. So I have the two driving forces here are the heating from the sun and the force of gravity to bring it back down. And so water, it could come from the ocean, it could come from a lake. Anywhere that you have surface water can evaporate, go up into the sky and precipitate anywhere, but that's how you move water into the mountains. One of the things that actually concerns me, I'm at the top of a mountain, I have a well. Well, what's feeding that well? Water runs downhill, and so the only thing that can be feeding that well is rain. And so this year we've had a lot of moisture. We'll probably have a good water table right now. But in drought years, it seems like I'm in a precarious situation because I can only have water coming down from above to feed my water needs. The specific processes, evaporation. So define evaporation. They're putting in the TV monitors. That's what they're doing. Go ahead.
Like the heat from the sun causing the water to rise.
Well, evaporation is not the rising. What did you say?
Said evaporation is a liquid turning into a gas.
Okay, liquid into gas. Is that a chemical change or a physical change? It's a physical. It's still H2O. The chemical hasn't changed at all. But it's evaporated. It's gone into a gas state where it's in the atmosphere. Precipitation, what's that? Okay, so it's rain, which is gas to liquid, yes. Now, precipitation doesn't mean gas to liquid, right? That's condensation. But you have to have condensation for precipitation to occur. And actually, it's more complicated than this. My understanding from going to a weather training thing is that it actually always turns into ice and then falls as ice and melts. Infiltration. There's a word we haven't talked about. What does it mean to infiltrate? Okay, to enter. To sneak in is what we usually think, the spy infiltrated. The Jesuit spy infiltrated the Andrews University religion department.
Did that really happen?
No, not that I'm aware of at the very least. But lots of people say that.
Yeah.
People say, Samuel Bakioki, who got his doctorate at the Catholic, Vatican University. They say he's really a secret Jesuit. Well, he died a few years back. But I do not believe that to be true personally. There's no evidence for that. So infiltration is water going into the soil. And then we have runoff. What's the difference in infiltration and runoff? Runoff is running on top of the soil. And so here it shows precipitation to the earth, and then runoff is flowing over the surface, whereas infiltration goes into the ground. And notice it says infiltrates, not runoff, or not infiltration, because infiltration is going into the ground, and then you have the water that infiltrated, they call it infiltrates, going through the ground. We talked about the difference in porosity and permeability during our walk. So porosity is talking about pores, the open spaces in your soils. So some soils have lots of open spaces. For instance, if you have a sandstone, sand grains tend to be irregularly shaped, and when you pack them together, you're going to have lots of gaps between them. And so they're quite porous. Whereas if you have a shale is made from really tiny particles, so you squeeze those together and there's not much holes. And so what do we have here? We have clay. Clay soil is another thing that's very tiny particles, very tightly compacted. And so that clay soil does not have much porosity, doesn't have much places to store water. So that's what porosity is, the ability to store water. And so things with larger sizes for the soil tend to have higher porosity. Things with smaller sizes, lower porosity. And also the shape sorting. Sorting is the variation in size. If you have things that some are bigger, some are smaller, you're going to have a different porosity than if they're all bigger, for instance. Right? All bigger, you'd have more pores. Then permeability is how easily water can go through. Something can have lots of holes in it, like take a piece of, the lava stone. You have air bubbles that form in the rock. Air bubbles, let's just call them gas bubbles to be accurate. Those gas bubbles then create lots of pores that can hold a lot of water. The problem is, each of those little bubbles is completely sealed. So it's very porous, but not at all permeable, because water can't pass through it. So we care about permeability quite a bit, because if we want to have water flow through the ground, if I want to be able to put down a well and pump up water, I need to have water flow through the soil to get into my well. And so the permeability tells us about hydraulic conductivity, how easily water can go through the soil. Question?
Can you go back to the
porosity? Okay. Now we've talked about groundwater. Groundwater is water that's in the ground. Surface water is on the surface. Groundwater is in the ground. Groundwater is what we pump up with our wells. And the groundwater occurs in what's called the saturated zone. We've talked about saturated before. Saturated means it has as much as it can hold. So if you take, for instance, a potted plant and you pour some water in, what happens when you pour just a little bit of water into the potted plant?
It soaks into the soil.
It soaks into the soil. That means that the soil was not saturated, that it could still hold more water. But if you keep putting more and more water in, you saturate it, it's filled with water, any excess water then will run out. And apparently, how you water a plant, you're supposed to go somewhere between the two of no water and saturated. I don't have a green thumb to figure that out. So, well, the water table, this word right here, is the level between where you have saturated and unsaturated soil. So if here's my soil, and it's saturated up to this level, then my water table is that divider. And if I'm going to drill a well, where do I need my well to go?
Lower than the water table.
Lower than the water table. And I probably want to go a fair amount lower than the water table. So when you have seasonal variation in the water table, it stays below the water table, and then I can still pump water out. Any water that is above the water table is called soil moisture. So there's water above the water table, but it's called soil moisture in that case because it's not saturated. Now, we talked about the water tables. We were walking down looking at Holmes Lake, and I said that if you were to dig down right by the shore, when you get down to water level, you would have your hole starting to fill with water because the water table right next to a lake is going to be the same level as the water in the lake. But if you move away from the lake, it can move differently. So this picture shows it moving up if you go away from the stream. What condition would make the water table go up when you move away from the stream? There are two things you would need. One is you would need to have this soil here has a reasonably slow speed for water to go through, right? If the permeability is very, very high, then you pour water in, you pour water here, and within a day, the water makes it down here. If that's the case, then this is just going to be at the level of the stream. The second thing you need is that you need to have had a fair amount of moisture up here. Right? If you have moisture up here and it takes a while for it to move away, that's how you build a water table that's above the stream level. Here we have a well. They're down the water table, but that well is not going to do them well. Why is the well not going to be good for them?
Because if there's a drought, they'll run out of water and they can drill lower.
Yes, if there's a drought, the water table drops below their well goes dry. Now, one would think if this stream runs even in droughts, if they drill to a little below the stream level, they should probably be good even in a drought. So, how deep you drill your well is going to depend on the variation you have in that water table. You want to make sure you're always below the water table. Aquifers are just reservoirs. And so what aquifer did we talk about during our walk? The Ogallala Aquifer. Now, I totally should have already had the Ogallala Aquifer loaded up here. I have something else loaded up, but I don't have a picture of the Ogallala Aquifer loaded up, so I'm going to have to load it up now. So we'll just go with that picture for now. There's different pictures you can find. But as you see, this Ogallala aquifer is huge. Now, come on. And basically all of Nebraska is over it, or it's under virtually all of Nebraska. We have a huge, huge underground pool of water. Now, when I say it's a pool of water, if you were to dig down into the aquifer, what would you find?
Water.
Okay, water, what else?
Sand, dirt.
Yeah, you'd find soil that is permeable, has a reasonable porosity so it can hold a fair amount of water. It's permeable so the water can flow through. It's not an empty chamber. If it was an empty chamber, it'd probably collapse, right? So it's filled with soil, but it has all of that water. So that's an enormous resource. And that's why I am opposed to having oil pipelines cross that. Because if you pump a bunch of oil, I don't actually remember the path, and I forgot that I can't draw on this, but it was going something like that. If you pump a bunch of oil through pipes and a pipe breaks in there, you're going to have a huge amount of oil then in that aquifer, and you're contaminating this important water resource. Not trying to be political here, but trying to point out some ecology concerns that I have. It is important to keep this vital source of fresh water clean and contaminant-free. That came from the textbook, I believe, even though I wholly agree with it. All right, artesian springs and wells. We talked about these on the walk as well. Artesian wells, or artesian springs, there's really no difference as far as I know, are you dig a hole in the ground and water comes out. I think the difference in the two is an artesian spring is natural, artesian well, you dug it. I think that's the difference in the two. And at first blush, it seems that shouldn't be. Because if the water comes springing out, what does that tell you about the water table? The water table is above ground level. So why aren't you in a stream if the water table is above ground level?
The soil won't allow the water.
Right, the soil is non-permeable. It won't allow water to go through it. So if you punch a hole where water can get through, it comes up. And then of course the question is, how do you get a situation where the water table is higher than the ground level? And gravity has to be what's doing that. And Bryson, I think, talked about, hence the water towers for supplying water pressure in a city. So here you have, it rains and snows up here. You have water in your aquifer. This is the level. As you go through, because there is some resistance to water flowing through the soil, that's why this table doesn't stay at the same height. It's dropping because there's resistance to water going through. But the pressure is such that the water table would be here, and hey, here the water table is above ground level. If you punch a hole through, water comes up.
It sounds dangerous. You're like drilling a well and water spurts up.
They have this situation when they drill for gas, natural gas.
Yeah.
That's much more dangerous because that's, it burns.
Right.
Burns rapidly. Hence I was going to say explosive. This here, sure, you're going to have some backwash and you want to make sure you're not, I've got the shovel here, but it's not as dangerous. Hence we don't have water wildcatters, Few more words here. A perched water table. Perched water tables are interesting beasts. So that picture shows a perched water table where you have an aquifer that's above a region that is not saturated. Now, if you think about it, all aquifers actually have a region below them that's not saturated. It's not saturated all the way to the center of the earth. But how do you get that perched water table? Well, you just have to have something, going again with what Hosanna just told us, something that's not permeable down below it so the water can't sink down. Because the water is going to go slowly through the soil, if you have a big enough non-permeable permeable barrier below, you'll build water above it, and so that's a perched water table. So for instance, a person could put a well down into this, and they would be fine as long as it's going to rain enough to refill that. If it doesn't rain enough, this is easily going to disappear. And we see evidence for these in things like springs. Hydraulic head, not a question, right?
No.
Okay.
Sorry.
I want to be responsive to students. Hydraulic head is a term for how much water pressure you're building. And the hydraulic head then has to do with the difference in elevation. And so here you have a difference in elevation between the water table and where you are of, I think, 40 minus 415 is 25. So you have a 25 meter water head, which is telling you about how much pressure you would have coming out. Now I have here Darcy's law. The rate that water flows is the product of the hydraulic conductivity, how easily water goes through the soil, which is a measurement of the permeability, multiplied by the cross-sectional area, how big the region is that the water can go through. Think of it as a pipe. What's the area of the pipe? Small pipe, big pipe. Times the hydraulic gradient, which is the rate of change of elevation. You don't need to use this for anything. I'm not going to give you numbers and have you fill it in. What you should know is the things that are going to affect the rate at which water flows through the ground is the pressure difference, hydraulic gradient, the area that the water can pass through, and how permeable the soil is, the hydraulic conductivity. So make sure you have those three things are what the ground water flow rate depends on. You don't have to be able to use it. You have to know those are the important factors. Clear enough? Bryson and Amber say yes. They represent the whole class. Oh, no, you did already. You indicated yes. I wasn't trying to force you to. Okay, what's this? Yeah, that's the pothole in Lincoln, right?
Yeah.
They seem that way, but of course that's not a pothole in reality.
There are panes inside of it.
Oh.
Okay, you want to explain, Jose?
Oh, it's at the top. I
it's
see.
like
It fell. Okay.
It just fell.
I thought it was just some really lazy worker.
Worse than the Lincoln ones. Just kidding, right? No, this here is not a pothole. It's not caused by what causes the potholes. We talked about that a lot. What causes them?
Expanding and contracting water.
Water. Water gets into cracks, it freezes, expands, and pops stuff out. That's not what caused this. This here, go ahead. This here is a sinkhole that was caused by water flowing underneath the road. I always suspect in something like this that it's probably municipal water rather than natural water. You know, they had a pipe that sprung a leak. And the water flowing can wash out material. It can dissolve. If you have something that's limestone, it'll dissolve the limestone. So if you've been to Tennessee and been to, was the Mammoth Caves? Is that?
Yeah.
You have a place where you had water flowing underground, and it dissolved the largely calcite soil, leaving these huge caverns.
They actually use the water that flows in those caves to feed their racehorses because they think the minerals in the water are really healthy. Okay. And so they feed the horses that are in the Kentucky Derby with that water.
Interesting,
yeah.
Interesting fact. So you have water that flows underneath and it can create a cavity. When it creates a cavity, then you have problems. And so in this case, the first thing that was noted was, why do you have stripes painted in the bottom of the sinkhole? And no, it's not lazy municipal workers who just drove over, didn't pay attention to what you've seen the pictures of, like a dead cat that has a stripe going over it. Because the municipal worker just wasn't paying attention. Straight line, right? course, then you see the other ones that are curving because who knows what they were doing, eating a sandwich. So in this case, and if you look, you see you've got here, looks like more cavity going that direction, but you washed out a bunch of soil or dissolved the soil and washed it away, and everything sank. So that's something water does. That's natural, or it could be because you had a blowout in a pipe.
But how do you fix it though?
Okay, yeah. How you fix it is a good question. It depends on the source. If this was because you had a water main that broke and had water leaking and it washed stuff away, you fix the water main, you refill, and you're good. If it's an underground stream, you have a little bit more of a problem because you're going to stop the underground stream.
Like a dam.
Yeah,
An underground dam.
it's going to be harder. You obviously are going to want to refill, and refill with something that's not likely to be washed away. But what you're doing is putting a Band-Aid on the problem because the water's just going to go somewhere else. It's not going to stop the water.
Just move.
It's just going to go somewhere else and wash out somewhere else if it's an underground feature. So that's why we have civil engineers. Civil engineers who figure out ways around that.
Big bucket.
A big bucket, yes. That's a good plan. Now, subsidence. I'm from California, and this is a real significant issue. What do you guys know about California? And let's stick to things that have to do with geology. We have drought. We have lots of droughts. And that's actually getting right into what I'm going to talk about. But what else do you know about the geology of California?
There's gold rush.
Okay, gold rush. Lots of minerals. And gold being the one that we care about the most. Lots of silver and Nevada. What is that?
There's wineries in the north.
Okay. There's a lot of wineries in the northern regions because the environment creates apparently grapes that make good wine. So, in the area of Pacific Union College, there's a lot of wineries and growing grapes for wine. One thing that you may or may not be aware of is California is a very fertile place. Lots of agriculture. My parents have 40 acres, very small operation, of almond trees.
Small.
Well, yes, it is. I will just show you so you can understand how small our operation is.
40 acres is a lot.
No, it's not.
Yeah, my uncle farms
Like
3,000 acres.
Yeah, his uncle's got a much bigger operation than us, for sure. So here is, okay, so let's get to the satellite view. We can close that off. Come on, satellite view. Okay, so remember I talked about the canal. That's the canal that borders our property here.
Why is that?
And so-
water?
Why is- what?
Turquoise. That water. Yeah.
That's our evil's little. Oh no, he is evil. He threatened to sue us because he said that the city put the road the wrong place. The road is supposed to be on the boundary line between us, on the center. He said, "Oh, the city put the road wrong, and I'm going to sue you, or I'm going to farm the last 2 rows of your orchard."
Dude, we should talk later. My parents have almost the exact same problem.
So we paid his bribe.
Seriously?
Seriously. So this is our operation right here. That's our 40 acres. Actually, yeah, that's our 40 acres. This is my uncle's 40 acres right here. As you can see, we're a small operation. That's all almonds or walnuts. Yeah. So that was not a point today. Just, 40 acres is a small operation when it comes to agriculture. How big did you say your uncle's was?
He has 3,000 acres.
Yeah, 3,000 acres. That's a few sections right there. Ours, no, we're not a section.
Most of it.
We're like an eighth of a section or something.
Most of it is just cattle pasture, but he farms 1,000 of corn. So,
Only 1,000. Okay, so in California, we have a huge agriculture industry. But we had, the first thing that was pointed out was Hannah saying we have drought. And so what do? Well, you get water wherever you can. And so the Central Valley, very fertile Central Valley, they put in wells and they pump water from the ground. But they pump it at a much faster rate than it gets replaced. And so you had all of this soil that was saturated, and the water actually helps to keep it from compacting. When you pump the water out, it compacts more. As the soil compacts, you have subsidence. The soil sinks. And so here's a region where you have ground level in 1977, 1925. The subsidence has been, I can't remember, 9 something. I'm guessing it's 914 feet in just 77, 25, roughly 50 years, 52 years. That's a lot of ground sinking because the water was pumped out. And of course, that's a big concern because the aquifers have been depleted, the ground sunk, and if you try to put water in there, it's now not going to accept as much water. So it's not like you can pump them back full. It's just not going to work. So, in my home, that's a real concern. Humans have taken away a lot of this usable water, which means California for the future is not as good as California for the past. I've already talked enough about that. This is showing how you can develop caverns and whatnot. So here is a stream, and you may or may not see the stream. A stream flowing. I meant to choose blue and chose green. A stream flow. Flowing through the ground. As the water seeps out, this stream is running through soil that's largely limestone in this picture. But limestone, calcium carbonate, is water soluble. Now, what is it more soluble in? The test that Hannah used?
It's more soluble in.
What did Hannah put on it to make
Acid.
it acid? So if you had acidic water, it would be more soluble. But water, remember, it's the one we consider neutral. But you will have water causing dissolving as well. And so the ground itself is being broken up by this water. And then the broken up water has soil that fills in. So you can see features forming like right here, where you had, because of the dissolved soil, the ground collapsed a little. That's basically how a sinkhole occurs. And you also notice, because this is water-soluble soil, the stream dug deeper and deeper. Now, if it's not water-soluble soil, the stream will still have a tendency to dig deeper, just not nearly as quickly. Actually, I'm not talking about those today. Don't put any questions about karst features. Let's get to streams, because we've got 10 minutes. I'm going to make it there. I want to talk about the floods and how they've affected things around here. So first thing about streams. If you have a stream, the water flows faster where it's deeper, slower where it's shallower. And when you have curves, the water tends to flow outside. And so where it's flowing faster, it's more likely to pick up and erode. And, well, you already have weathered soil, but weather and erode the material. And so as this stream flows, it's going to erode back on the outsides of the curves, and it's going to deposit on the insides of the curves. So you have these little sandbars often, which is where the stream has deposited material as it's moved away. But what happens to the shape of the stream? If the stream starts like this, and over time, it's going to go like this, something that started as a fairly straight stream will end up going like that if you have a reasonably flat valley. So we call a stream that does this a meander. And these meanders will meander back and forth through their meander valleys. And we'll see some pictures that show the significant changes that these cause. Unfortunately, I forgot. I have this completely out of order. Drainage basins. How many people have been to the Continental Divide? I suppose I have. Didn't pay attention. I've been to many different places, Continental Divide. Most recently, Monarch Crest is on the Continental Divide. And when I was your age, I was like, it must be something that divides the continent, the end. That's how much curiosity I had about it. Well, the Continental Divide is specifically about water and drainage. You have water, rain, that falls in the mountains. And when that rain falls, it's got to go somewhere. And the Continental Divide is dividing where the water goes. So if it's west of the Continental Divide, it ends up in the Pacific Ocean. If it's east of the Continental Divide, it ends up in the Atlantic or the Gulf Coast, which I consider part of the Atlantic, but I'm probably wrong. So that's what the Continental Divide is. It's separating where the water flows to. So, as I said, my house is right there near the Continental Divide. We're right near the Arkansas River. The Arkansas River, where my house is just to the right of it. So the Continental Divide separates the drainage basins. So you're never going to have water from the Colorado River mixing with water from the Mississippi or Missouri. If you look here, the Snake River and the Missouri River, they start at very close to the same points. But one's on one side of the Continental Divide, one's on the other, so they go opposite directions. So the Missouri comes over here and it flows right by, it separates Nebraska from Iowa and then joins the Mississippi and goes down there into the Gulf, whereas the Snake River flows into the Columbia River and into the Pacific Ocean. So that's what the Continental Divide is all about. How many people knew that's what the Continental Divide was and I just wasted your time? Just one. Good. So the other six, okay. Jessica too. Erosion deposition. We've talked about weathering and erosion quite a bit. So remind me once again, just a reminder, not something new, what is the difference in weathering and erosion?
Weathering is when you're like walking on a path or like it's so. The difference between weathering and erosion is that like weathering is when the eroded things get messed up. Is that kind of no?
Isn't it like weathering is like the breaking up of the stuff and the erosion is like the moving of it?
Right.
Yeah.
So weathering is breaking the soil or rock apart. Erosion is transporting. Faster water does more erosion. Faster water will pick up bigger pieces of soil and transport them. Deposition occurs when the water slows down. So fast water is going to do a lot of erosion, slow water, a lot of deposition. That's why, and I think I repeated this picture here. Nope, not yet. That's why in this picture you had deposition of the sandbars because the water is flowing slower there. You had erosion on the outer banks because the water is going faster there. Which one? This one? Okay. Another thing to know, and this is simple words, important concepts. Turbulent flow is when the water is doing a lot of tumbling. Laminar flow is when the water is moving as smooth layers. By the way, notice when I took a shower, my hands finally got unglued. So when you have laminar flow, you have smooth water. Turbulent flow, you have a lot of tumbling, and that tumbling is likely to pick up stuff. Streams are responsible for carrying a lot of stuff, a lot of sediment from one location to another, and laminar flows only pick up this. I'm very bad at clicking. Carry only the very smallest and lightest, whereas turbulent flows will carry much bigger things. When I was a kid, anytime we saw things like this, I said, oh, that was the Indians with their coming out and grinding up stuff with, the mortal pestle idea. My understanding is they did use that, but most of these are simply caused by water. You have water flowing over the rock. You have some rocks in a little cavity, and the rocks swirl around. And as they swirl around, they're grinding on the edges, and that's what makes those cutout shapes. So that's the result of heavy water flow and these rocks going around in there and grinding out the hole. So it starts with little sand-sized rocks and may get bigger as shown in this picture. And abrasion is what you call it when you have particles scouring the channel like that. So that's an abrasion activity. I need to get on to things. If you look at this, where is this? I am pretty certain this is Yellowstone. It's not Yosemite. I know Yosemite pretty well. I've been to Yosemite's waterfall once, and I'm pretty sure that's what it looked like. Or not Yosemite's, Yellowstone's. Yeah.
I've been to Yellowstone.
And so if you look at this, notice that it's a V-shaped valley. V-shaped valleys are cut by water. Water cuts V-shaped valleys because of just the way it's eroding the material. So when you see a V-shaped valley, you can usually say, that must have been caused by water erosion. Compare that to Yosemite's valleys, which apparently I don't have a picture of. But if you have glacial valleys, you can see I'm hitting it and it's just not changing. Glacial valleys are U-shaped. So if you look at a valley and the valley is shaped like this, it was more likely carved by a glacier. If it's shaped like this, it was more likely carved by a stream. So as you go someplace and you look at these features, you can actually identify, hey, this must have been a place where there were glaciers based on the shape. Now we're getting back to the meander idea. So here is some graphics of a place with a waterfall and then a flat region. And so the waterfall, of course, is going to cut back and move back in time. And the stream, you see, originally the stream was just going in this path, but over time the stream would have expanded out. And so it is expanded out, so you can see now the stream has covered all of this range here. And the waterfall has dug back, so it's cut back there. And so it's a flat valley where the stream has meandered back and forth. And then you get these cool things here that are called oxbow lakes. What would cause that oxbow?
Because the water table goes all the way up there, but the ground is thicker, so the water stays.
Okay, the water's there because of the water table. That's a good identification.
But those areas, the water comes up.
But what caused them, and so here's a picture of an actual meander lake. What causes them can be seen right here in what's going on right now. Notice this is March 16 of this year. That is very recent. And this is a year ago. Oops. Well, that actually works out okay. because I wanted to go here. I have this opened up. Want this to be full screen. This here allows us to compare what it looks like right now with what it looked like a year ago. And so that's what we had a year ago. This is what we have now. Look how wide the Elkhorn is compared to what it was. And the feature right here that we're focused on, which is also on this, but I'm going to go back to the picture here. You have this here is washed out. The stream was going like this. But when it washes out, now we're having water come like this. And there's a good chance that as the water level recedes, the stream will continue along this path. And this will form an oxbow lake out here. And we have some good examples of oxbow lakes. For instance, if I do go back to the web page, and I know it's now time for me to end. Not sure how effectively I can zoom in here. You see that right there? That's Carter Lake. The boundary between Iowa and Nebraska was drawn along the Missouri River. And when it was drawn, the stream went like this. The Missouri River went like this. Can you see where I'm drawing? And because it went like that, that's where the boundary is. So everything inside of this region here is Iowa. But you can't get there from Iowa because the stream has cut it off. So there's this Oxbow Lake that's Carter Lake, and you have the airport is right here. So the airport is both east and west of Iowa. It's in Nebraska. And people who live here in Carter Lake, they're part of Iowa. They pay Iowa taxes, etc., even though they are fundamentally in the city of Omaha. All right. Have a happy Sabbath.